Okay, here we go with the Chapter 5 homework review, the first of two Chapter 5 homework assignments. As I'm showing here, the average on this assignment was a 9.81 out of 12. So still not bad, although it is progressively dropping as the semester goes on, which is what usually happens. This was the first assignment where we had a lot of numerical questions, and that's all I'm going to be going over today are problems of that type. So in that, in this case, you need to get used to doing these types of problems, and if you have any questions about them, please come see me. And the other thing that sometimes causes a little bit of difficulty with these is there's a lot more of the free response type problems where you have to enter in the answer as a number, and so these have a lot less margin for error because you can't possibly guess right in most cases. So let's go through some of the questions people have. Some of these are requests from students, other ones were ones that I identified as problems we had trouble with. Alright, so this first one, there's a few problems of this variety, and we struggled with all of them. So here it says a mineral contains only a metal M and fluorine. If analysis indicates that a sample of the mineral contains 5.73 grams of M and 2.26 grams of F, what mass of fluorine is present in 14.5 grams of the mineral? Now this was a problem that had variable inputs for the different masses, so you may have gotten different numbers in yours, but a lot of people had this problem and a lot of people did not do so well on it. And as it turns out, this question here is really just a review of Chapter 1. We talked about mass ratios and mass percents way back then, and there's really nothing here that has to do anything with number of moles, and we can't really use moles to help us solve this problem because we don't know the identity of the metal M. If we knew the identity of M, then we might be able to do it in kind of a convoluted way that involves converting things into moles first, but if we don't know what the metal is, we can't calculate number of moles from that. So all we're going to do here is just use mass ratios as a conversion factor, something we did back in Chapter 1. So we're looking for the grams of fluorine that are present, and we're told that we're given a 14.5 gram sample of the mineral. I'll abbreviate that as MF, whatever the formula is, but some metal and some fluoride ratio. And then we're told initially that if you have a sample of the mineral contains 5.73 grams of metal and 2.26 grams of fluorine. And so what that means is that if we have 5.73 grams of the metal and 2.26 grams of fluorine, by conservation of mass, we would have the sum of those two, which is 7.99 grams of the metal fluoride, whatever the mineral is. So what this tells us is that now we have some potential conversion factors and ratios we set up. For every 7.99 grams of the mineral, we have 5.73 grams of metal, 2.26 grams of fluorine. What we're looking for is the mass of fluorine in the sample, so we're going to use that as our ratio. We want the mass of the mineral to cancel out, so we're going to put the 7.99 in the bottom. And then for those 7.99 grams, we have 2.26 grams of fluorine. So this ratio allows us to convert the amount of the mineral we have, 14.5 grams, into an amount of fluorine in that larger amount of sample. Now we could have also used these numbers here, the 5.73, 2.26, and the sum of those to find mass percents or mass fractions. If you wanted to do it that way, that would have been an extra step, but it would have worked. But instead, we could just use the raw numbers that were given and use those as the numbers in our ratio. And so when we multiply this out, it's a relatively simple problem at this point, just to multiply and divide. And with this set of numbers, we would get 4.10 grams of fluorine. Okay. And then since this is a Blackboard problem, you just enter in the number 4.10. I believe this is a free response type problem. Alright, so it's important not to forget things that we did a while ago and not to try to make them more complicated than they are. This problem appeared on Chapter 5 homework, but it was actually really just a question we could have had from our knowledge in Chapter 1. Now the rest of these, though, are based more on the new stuff. So this question, I believe, was a request from a student. It's a relatively straightforward conversion. So we have Roundup, which many of you probably use in your backyard to control weeds. It has the formula C5HW1. We want to know how many moles of molecules are there in a 783.5 gram sample. Now this terminology here, moles of molecules, is perhaps more verbose than it needs to be. Really this is just asking how many moles are there. Okay? So this is a molecular compound. It's all non-metal elements, so it's a molecular compound with this formula. And so when you convert grams into moles, what you're really saying is how many moles of molecules are there. So that maybe that terminology threw a little people off, moles of molecules. It's just a really unnecessarily long way of saying moles. So from there we just have to convert this mass amount into moles. If we're given mass, we need the molar mass to be able to do that. So we need the molar mass, or the molecular weight, of this C5HW1 compound. And so we're just going to add up the individual atomic masses. So we have 3 carbons, and we need to find its atomic mass on the periodic table. So carbon here, we've seen this one a lot already. Carbon is atomic number 6, but we need the atomic mass, which is 12.011. That's that number below the symbol. So we have 3 carbons at 12.01 grams per mole, and then we have to calculate the contribution from hydrogen. We have 8 hydrogens. Hydrogen is the simplest element, and it's a 1.008. So that's the contribution from hydrogen. We have 1 nitrogen, and then nitrogen is 14.01, so I won't go back to the periodic table, but that's, again, all of these are the individual atomic masses of the elements that we're using. So carbon, hydrogen, nitrogen. And we'll go down to a second line here. We have 5 oxygens. The atomic mass of oxygen is 16. And then we have 1 phosphorus. I believe that's 30.97, but I'll check on that so I don't give you the wrong number. Let's go make sure phosphorus is actually 30.97. Phosphorus 30.97, and so that's the atomic mass of phosphorus we're going to use. And so we just add all these terms together. So 3 times 12.01 plus 8 times 1.008 plus 14.01 plus 5 times 16 plus 30.97. As long as I didn't screw anything up, I got a molar mass of 169.07 grams per mole. So that's what we're going to use as our conversion factor to go between grams and moles. And so then finally, if we want the number of moles, we have 783.5 grams of C5HW1, and then we want to convert grams into moles, so we want moles in the numerator, grams in the denominator. So we're going to put this number here in the denominator, make sure that grams cancel out. That's per 1 mole. Alright, so we're just basically dividing the two numbers. And we get 4.634 moles. I think this might have actually been a multiple choice question. I didn't put all the answer choices here, but that would have been the number you would pick, whether it's multiple choice or free response. Okay, so that's how we do that one. A pretty simple, straightforward grams to moles calculation. And this type of calculation is very important because we're going to use it a lot, not just by itself as we did here, but also as parts of other types of problems that we'll be doing later on, especially with stoichiometry that we just started introducing. Okay. Next question here, also request from a student. So we're talking about isotopes now, and so we have 2 isotopes of neon, neon 20 and neon 22. The way that we write this is the same as putting, that's the mass number when we have these numbers afterwards. So it's going to be, these are the symbols for that in case that was confusion to anybody. So it's neon 20 and neon 22. The atomic mass of neon is approximately 20.2. What are reasonable estimates of the relative percentages of neon 20 and neon 22 respectively? Now this question is leaving out a lot of the nitty-gritty details, but what it's basically asking us is if we have 2 isotopes, 20 and 22, and the atomic mass is 20.2, what's the relative fractions of those? Now there's a couple ways we can help ourselves out here. Remember that the atomic mass that's on the periodic table, which we're being told is approximately 20.2, is the weighted average of the isotope masses. So it's going to be the fraction of neon 20 times its mass plus the fraction of neon 22 times its mass. Alright, so whenever we have an atomic mass, it's a weighted average of all of the individual isotope masses. Alright, so that's kind of the equation we're going to use. And so the atomic mass is given to us, and we're going to try to find the fractions of each, or then convert those into percentages, really. But we're missing here, and we have the masses of the isotopes that we need as well. Now, before we even start looking at the numbers in more detail, we see that the atomic mass is 20.2. The two isotopes are 20 and 22. So we're not told the exact masses of the isotopes, but if we're not given the masses, we can assume that the masses are very close to the mass number. So the mass of 20 neon is very close to 20 AMU. It won't be exactly that, as we talked about, because of E equals mc squared, but it's going to be really close to that. And so the mass of 22 neon, the other isotope, would be about 22 AMU. Okay, so those isotope masses weren't given to us, but if they're not given to us, we assume that they're approximately equal to the mass number, which is a good approximation to make. And then finally we have to keep in mind that the sum of the fractions, so the second equation is really going to be that the fraction of 20 neon plus the fraction of 22 neon, the sum of those has to be equal to 1. There's only two isotopes. Alright, so we have two equations, two unknowns, we have the masses here. Before we start doing algebra, we can help ourselves a little bit and get rid of some of the answer choices. So we notice that the atomic mass is 20.2, which is much closer to the mass of the neon 20 isotope than it is to the neon 22. So when the atomic mass is much closer to one isotope versus the other, we would say that that isotope has to be the most abundant. So because the atomic mass is close to 20, that means the 20 neon isotope is the most abundant. And so this is asking here the estimates of the percentages of neon 20 and neon 22. Neon 20 should be the more abundant isotope. So choice A, B, and likely choice C we can eliminate, because in those cases the neon 20 is not most abundant. And then the question becomes, is 80-20 or 90-10 the more reasonable ratio? That's probably going to be hard to do in our heads, so we'll have to set up the problem to get those. We can eliminate 3 of the answer choices because we know just from the atomic mass being close to 20 that the neon 20 isotope has to be the more abundant one. So that's going to help us out for solving this question. But now we have to go in and do the algebra. So let's call the fraction of neon 20 x, let's call the fraction of neon 22 y. And so what we have then is that this atomic mass of 20.2 is equal to 20, which is the mass of neon 20 times its abundance x, plus the mass of 22 neon, which is approximately 22, times y. X plus y equals 1, and so that means y equals 1 minus x. So we're going to put that up into here. And so our new equation, just in terms of x, which is what we're solving for, is 20x plus 22 times 1 minus x. And then doing a little bit of algebra. Give me a second here because I didn't do this ahead of time. Sorry, hang on. I got x equals 0.9, which is 90%. So that means the abundance of the neon 20 isotope is 90%, the other one would be 10%, and so choice E is the correct one here. So both choices D and E were reasonable based on the given information. One thing we should keep in mind is if the percentages were 50-50, I didn't mention choice C specifically, but if the percentages were 50-50, the atomic mass would be exactly in between the two, or 21. So it's still close to 20, so we know that neon 20 is more abundant, and then the math tells us that choice E is the more reasonable one. Okay, so whenever we have isotope masses and atomic masses and the relationship between those, is going to be these types of equations. The atomic mass is the weighted average of the two, or however many more we have, and then the sum of all the fractions has to be equal to 1, or alternatively, the sum of the percents has to equal 100. Alright, this problem here asks us to do a bunch of calculations involving moles, and we want to know which of the following has the greatest number of atoms. So we have 1 mole of helium, 0.60 moles of H2, 20 grams of potassium, 8.5 milliliters of H2O, 22.6 grams of KMnO4. So we have a lot of different conversions to do here. So let's just do them all and see which one has, we're looking for greatest number of atoms. So in choice A, the number of atoms is going to be, we have 1.0 moles of helium. Helium is a monoatomic element, so if we just multiply that by Avogadro's number, 6.02 times 10 to the 23rd atoms in 1 mole. And so this is just going to have Avogadro's number atoms. Alright, so choice A is Avogadro's number. We could have done that one in our head because it's just 1 mole, and 1 mole of anything has Avogadro's number. Now for choice B, we have to be a little bit careful here because we see this 0.6 moles. So we might say, oh, that's got to be less because it's 0.6 moles for choice B, 1.0 moles for choice A. However, we're looking for moles of atoms here. So if we have 0.60 moles of H2, key phrase being there that is dihydrogen, H2, we can multiply that by Avogadro's number, but that's going to be molecules of H2 per mole. Alright, because H2 is a diatomic molecule, so the number of molecules is going to be Avogadro's number. And then if we want the number of atoms, there's going to be 2 atoms for every molecule of H2. Alright, because it's H2, so each molecule has 2 atoms in it. And so really when we do this and multiply it out, we get 1.2 times Avogadro's number, which is 7.23 times 10 to the 23rd. Alright, so choice B is bigger. We're looking for the greatest number, so choice A we can eliminate because choice B is bigger than it. And so the rest of these we have to do similarly. So for potassium we have and then for this we need to use the atomic mass to convert from grams into moles first. So here we're given a mass. The last 3 we're not given number of moles directly, so we have to convert into moles first to be able to use Avogadro's number. Potassium has an atomic mass of 39.1. I'll just call it 39. We don't need real precise numbers here for this problem. So it's approximately half a mole, and then we're going to multiply that by Avogadro's number to get number of atoms. So once you have moles, multiplying by Avogadro's number gives you the number of fundamental particles that are in that sample. Again, potassium is a monoatomic element, just K, so multiplying the number of moles by Avogadro's number gives us directly the number of atoms. So in this case it's going to be about half of Avogadro's number, so it'll be smaller than the rest. If you want the exact number, it's something like 3.1 times 10 to the 23rd. Alright, so smaller than both of the previous ones. We can get rid of that one as a choice. Choice D may have been the one that people got tripped up on. We have 8.5 milliliters of water, and we don't have any relationships right now that relate milliliters into moles. So how do we deal with this one? If we're given a volume, 8.5 milliliters of H2O, we should remember density. That's one thing that we haven't talked a lot about, but is in the review part of this course, so it's something that you're expected to know already. And so if we have 8.5 milliliters of water, we can use the density of water to calculate the number of grams of water, and then from there we can go into moles, as we know how to do. The density of water is the only one that you should know, or at least have memorized, which is 1. So there's 1.0 grams of water in 1 milliliter. Alright, so if we have 8.5 milliliters of H2O, we also have 8.5 grams, and then from there we can convert into moles. And we're going to use the molar mass of water, which is 2 times hydrogen plus oxygen, or 18. Again, we don't need to be real precise for this problem, so we're just comparing numbers. And then if we have moles of water, we're going to use Avogadro's number. That's going to be molecules. because water is a molecular compound. So when we use Avogadro's number, that gives us the molecules, but then if we want to convert into the number of atoms, just like we did for H2, we figure out how many atoms are in a single molecule of H2O. So H2O has 3 atoms, 2 hydrogens, 1 oxygen, so it's going to be 3 atoms in every 1 molecule. And so when we multiply this out, we get 8.5 divided by the molar mass times Avogadro's number, and then times 3, because there's 3 atoms, and this one we get 8.5 times 10 to the 23rd. And that looks like the biggest so far, 6.02, 7.23, 3.1, 8.5. So that's the biggest one so far, so we can eliminate the other answer choice. And we finally have to see what choice E has, how many atoms are in there. This is a good problem because it gave us a lot of practice on using these types of conversions, and they're all a little bit different in this case. So we have 22.6 grams of KMnO4. We have to convert that into moles. So we use the molar mass. Let's see, 39 plus. So the molar mass of KMnO4 is approximately 158. So I did that quickly. So we're using its molar mass of about 158. Now this is technically an ionic compound, so we have, for Avogadro's number, we have 6.02 times 10 to the 23rd formula units. So a formula unit is basically the empirical formula of an ionic compound. So you have 6.022 times 10 to the 23rd of those per mole of KMnO4. And then, like these other ones, we have to figure out how many atoms are in one of those formula units. So it's KMnO4. We have 1, 2, 6 total atoms. Potassium, manganese, and 4 oxygens, a total of 6 atoms. One formula unit. FU is not the greatest abbreviation for that, but that's what I'll use. 22.6 divided by 158 times Avogadro's number 1 times 6, we get 5.2 times 10 to the 23rd. So this one's a little bit smaller than most of the others, so it's not going to be our answer. But we had to do a lot of steps here. We had to convert grams into moles, moles into number of molecules or formula units, and then for many of these we had to also account for how many atoms there were per molecule or formula unit. So a lot of conversions here, but this one comes out the biggest, so choice D should have been the one you picked. Okay? Alright, on to the next one, a pretty standard empirical formula question. There's a few more left. Okay. So a certain compound has 85.63% carbon and 14.37% hydrogen. The molar mass is 42. Calculate the empirical formula and the molecular formula. Now, for a lot of these, we can eliminate answer choices because if we look at some of these, so C5HW1, that's a valid empirical formula. Remember, empirical formula is lowest whole number ratio. So the difference between empirical formula and molecular formula is that the empirical formula is the lowest ratio of elements, and the molecular formula must be some whole number multiple of the empirical formula. So for choice A, C5HW1, that's a valid empirical formula because that's the smallest ratio, 2 to 3, and then C4H6 is just 2 times that. So that one could work. But then if we look at choice B, we're given an empirical formula of CH3 and a molecular formula of C3H6. Those two aren't compatible with each other. This is fine. This is a ratio of 1 to 3, but then the molecular formula should also be 1 to 3. C3H6 is 1 to 2, not 1 to 3. So that number, this answer doesn't even make sense at all because those two cannot be the empirical and molecular formula together. Okay, so if it was CH3, the molecular formula could be either CH3, C2H6, C3H9, but it cannot be C3H6 because that changes the ratio. Choice C is okay. If your empirical formula is CH2, your molecular formula could be C3H6. And then finally for choice D, this is another one that doesn't work out because, oh no, sorry, this one's fine. CH3, C2H6, those two are both 1 to 3 ratios. But then for choice E, you have C2H6 and C3H9. This is not an empirical formula. C2H6 is not the smallest ratio of 2 and 6. It should be CH3, so we can't use this as our answer choice either. So without even doing any math, we've eliminated 2 answer choices. Now there's actually a shortcut to this problem that I'll show you now. We have 3 answer choices left, and all of them have different molecular formulas. C4H6, C3H6, C2H6. So for choice A, C4H6. We're told that the molar mass is 42.0, so the molar mass of a compound with the formula C2H6 would be, C4H6 would be 4 times 12 for carbon. Then we have 6 hydrogens, which are about 1. So again, I'm approximating here. But if we had a formula of C4H6, we would get 54 grams per mole, which doesn't match the given molar mass that we're told, 42 grams per mole. So that one's out. For choice C, which is also could be reasonable, if we have C3H6. The molar mass of this is 3 times 12. We have only 3 carbons now. And then we have 6 hydrogens again, so 6 times 1 grams per mole for hydrogen. That comes out to 42 grams per mole. So the formula C3H6, that matches. If we do C2H6, the molecular weight, or the molar mass as it's called here, 2 times 12 grams per mole for carbon, plus 6 times 1 gram per mole for hydrogen would be 30 grams per mole. So this is the only one. Choice C is the only one where the molar mass matches what we're told it is. So that's going to be our answer. That would end up being perhaps a simpler problem. We didn't even have to figure out the empirical formula here because the only one of them has basically the situation where the empirical formula and the molecular formula match each other, and the molecular formula matches the molar mass. Now, even if you didn't see that, we could have also found the empirical formula with this information. And so to do that, if we have our mass percents are given at 85.63 and 14.37, so remember we interpret those as mass amounts and convert them into moles. I paused that by accident somewhere. Now the question is, how much of this did I lose? Alright, so that was I botched that a little bit. Well, in case I missed something on here because I accidentally paused the video, so up here what I have at the top is, I'm going to draw a little line between this, 2 ways to do this problem. We're told that the molar mass is 42 grams per mole, so the first thing I did was just calculate all of the molar masses that correspond with these potential molecular formulas, and the only one that matches is choice C. So on the basis of molar mass, we could have picked choice C. We didn't even have to worry about calculating the empirical formula. But an equally alternative and equally valid way to do this would be what I have here at the bottom, taking the mass percents of each of the elements, converting it into moles, and then from there you can find the empirical formula, something we did in class a few times. So there's 2 ways to get the answer to this, but both of them lead you to choice C. So hopefully I didn't lose too much of that video because I accidentally paused it there. Alright, this next problem here is pretty similar to one of the problems we had above, where here we're asked to calculate the number of chlorine atoms present in 27.5 grams of chloroform. And I had a lot of questions from students on problems like this, maybe not this exact one, but similar ones. And what always inevitably happens is that we forget a key step here. So if we want to find the number of chlorine atoms, we're given the mass of chloroform, which is 27.5 grams. As we've already covered in this review, we have to convert that into moles by using the molar mass. So we want grams in the denominator. And so we need the mass of 1 mole, so we add up the atomic masses of carbon, hydrogen, and chlorine. So carbon is 12.01, hydrogen is 1.008, and then we have 3 chlorines, which are 35.45 grams per mole each. So the molar mass of chloroform is 119.37. So we have 119.37 grams of CHCl3 in 1 mole, so the grams cancel out. And then from here, there's a couple ways we could do this, but we want to convert into number of atoms, so we should immediately think of Avogadro's number. However, when we use Avogadro's number here, as we talked about in an earlier problem, this represents the number of elementary particles in that sample. So chloroform CHCl3 is a molecular compound, it's a covalent compound. So that means when we use Avogadro's number, it represents the number of molecules in 1 mole. Okay? So whenever you use Avogadro's number, you have to think a little bit about what it means. Is Avogadro's number going to give us directly the number of atoms, or as is the case here, it gives us the number of molecules? So many of you stopped here, you multiplied and divided these numbers and got an answer that was close, but we forgot the last step. We're looking for number of chlorine atoms, and so if we have a molecule of CHCl3, the little 3 here tells us that there's 3 chlorine atoms in every molecule. So we have to multiply by 3 as our last step, and that's the step that a lot of you forget when you do these types of problems. So when we multiply and divide all these numbers, what I got was 4.16 times 10 to the 23rd chlorine atoms. And then the log of that, this is what we have to enter into Blackboard, is just going to be 23.62. So please don't skip that step. There's a lot of problems in this section where we ask you to take the log of your answer. So don't try to enter it in scientific notation. Take the log as we tell you to and enter that number in. It's going to be like that a lot on some of the test questions as well. So this question here, very similar to ones we did above, just have to remember this last step. And then the final one that I'll go through is another one that uses really the same concept that trips people up. So I think I'm going to do this one quickly. So we have a 0.1 mole sample of ethane. We want to know which of these does it contain, 6.02 times 10 to the 24th molecules, or different numbers of atoms are given as answer choices as well. So if we want to find the number of molecules to see if choice A works, all we have to do is take 0.1 mole of C2H6 and then convert that into molecules using Avogadro's number. So this is, again, a molecular compound, so Avogadro's number will tell us that there's 6.02 times 10 to the 23rd molecules in 1 mole, and that would be 6.02 times 10 to the 22nd molecules. So this sample has 6.02 times 10 to the 22nd molecules, which doesn't match choice A. The rest of these ask for how many atoms it has, so we need to do one more step. We can use this number as an intermediate, so we have 6.02 times 10 to the 22nd molecules, and then the formula is C2H6, so there's 2 carbon, 6 hydrogen, or a total of 8 atoms, and a hint was given to us that we have to figure out how many atoms are present in one molecule. There's 8 atoms per molecule of C2H6. And so when we multiply that answer, 6.02 times 10 to the 22nd times 8, we get 4.82 times 10 to the 23rd atoms, which matches choice B. Okay, so a lot of the questions we have trouble with had really that same concept involved. Once you use Avogadro's number, you have to keep in mind what that number represents. For a molecular compound, that will tell you the number of molecules. If you want the number of atoms, you have to consider the chemical formula and figure out how many atoms of each type or how many total atoms, depending what it's asking, are going to be in there. Alright, this last one was a little different, and I had a lot of questions on this one throughout the week as well, although it seemed like we did okay on the homework assignment, but I do want to cover it. So we have a metal oxide with formula MO, which contains 19.66% oxygen. We want to type the symbol for the element represented by M. Whenever we're doing a problem like this that asks us for an unknown element, the way we want to do it is we want to find the atomic mass of that element. There's going to be a lot of variations on these problems in the next couple of chapters. Chapters, I think, 4, 5, 6, 5, 6, and 7 all have problems of this type where you're asked for an unknown element. And in each case, what you're almost always going to do is find the atomic mass of that element. If we find the atomic mass of the element, we can go to the periodic table and then figure out which one it is. So when you want to find atomic mass, you need the grams of the unknown element, in this case M, and you need the moles of that. Because remember, atomic mass is the number of grams per mole. So if we know those two quantities together, grams and moles, the dividing the two, the ratio of the two, gives us the atomic mass. So if we want to find the mass of the metal, remember here we're given mass percents, so we're going to assume 100 grams of the compound MO. This is going to have 19.66 grams of oxygen, and then the difference on that, 100 minus 19.66, will give us the mass of the metal. Alright, so the sum of the two must equal to 100. We're dealing with percentages. So we have 80.34 grams of metal. Okay, so that's going to be the numerator up here, 80.34 grams. We're just assuming 100 grams using the mass percents directly. But now we need to find the number of moles of the unknown. And this is where we're going to use the given information in a slightly different way. So we only know the mass and the identity of oxygen. So we know that we can find the number of moles of oxygen in this sample because we have 19.66 grams of oxygen. We can use the atomic mass to convert from grams to moles, and we did many times today already. So we use the atomic mass of oxygen, which is, I'll be a little more precise here, 16.00 grams of oxygen in 1 mole. So we divide by that to get the moles of oxygen. And then what we know is the chemical formula is MO. So that means there's no subscripts on either element, meaning there's one of each. And so if you have 1 mole of oxygen, you would also have 1 mole of metal in there. That's what the ratio MO tells us. If it was M2O, we'd have a different ratio, but here it's just MO, which means from the chemical formula we know that for every mole of oxygen, there's also 1 mole of the metal. And so when we multiply that, we're just doing a trivial conversion by multiplying by 1, and we get 1.229 moles of the metal. So we put that up here, that's the number of moles we have. Grams per mole is 80.34 divided by 1.229, and that gives us 65.37 grams per mole. Alright, so this is the atomic mass of our unknown element. And then what we're going to do is go to the periodic table and figure out which element that corresponds to. Because obviously you're not expected to memorize all the atomic masses, but that's what the periodic table is for, or one of the things that it's for. So if we go to the periodic table, we got a mass of, what was this? Make sure I remember, 65.37, so somewhere around 65. And we see that that should be closest to zinc. Okay, copper is 63, zinc is 65.39, so we're really close to that. Gallium 69. It's the only one that's a close match is zinc, so that means our unknown element is going to be zinc, Zn, and that's the symbol you would type. Alright, that takes us to the end of this week's review. Please come see me with any other additional questions you have, and we will see you in class later today.